Okay, good afternoon, folks. Thanks for dropping by. My talk is about time and position spoofing with open source projects. And GPS is widely used for positioning and time synchronization for mobile devices. However, since time and position data of mobile devices are trusted and seldom verified by most vendors and developers, it provides a huge attack surface for potential attackers. In this talk, I will walk you through the methods of positioning and time spoofing simply with some open source projects. My name is Wang Kang. I'm a security analyst for mobile security team of Alibaba Group in China. Chen Shihua and Pan Naiming are co-authors of this talk, but they are attending the Double 11 festival in China, so they cannot come here today. Okay, in this talk, I will demonstrate the time and position data of mobile devices can be easily cheated using open source tools, and neither physical touch with mobile devices nor jailbreak root process is necessary. It's able to interfere all the position and time of cell phones in the surrounding area. Several years ago, it's still very expensive for personal potential attackers to obtain SDR devices. SDR stands for software-defined radio. But with SDR platforms becoming much cheaper, hardware cost of this method is only about $300 today and could be even cheap later. First, I will introduce and demonstrate a method of GPS signal spoofing with SDR platform. Then I will show a method of Wi-Fi based positioning spoofing. In our opinion, it's urgent to inform vendors and developers of mobile devices and the GPS and Wi-Fi positioning data are not reliable and should be verified carefully. In the end, some advices on preventing such spoofing are provided. Okay. Let's look at GPS spoofing. First, let us define the problem of GPS positioning. And there is a satellite at x1, y1, z1, and we can measure the time it takes for a signal to reach from the satellite to us, which is tau1. With the velocity of light c, we have this equation which says the distance from xyz to x1, y1, z1 is equal to c times tau1. We cannot solve it though, since it has three unknowns. So we can simply add another two satellites whose coordinates are already known too. Let's mark them as x2, y2, z2, and x3, y3, z3. And also, we can measure the durations tau2 and tau3, so we can get an equation set as shown in the lower right of this slide. Now it seems that our position coordinate x, y, z can be solved out of the equations. But it's not enough in engineering practice to measure tau1. We compare the time of receiving and sending of the signal. The time of receiving comes from our local clock, while the time of sending comes from the clock on the satellite. Those two clocks are not necessarily synchronized. There is a time deviation between them. We note it as delta T1. This gives us a new set of equations. Again, we cannot solve these equations since we have just introduced three additional unknowns, which is delta T1, delta T2, and delta T3. Now we have a good news and the bad news. The good news is the clock on different GPS satellites are high precision atomic clocks, which are strictly synchronized. So all these delta T's are equal. Now we have the following equations. But the bad news is we still cannot solve this equation set. We have four unknowns, right? And there are three equations. So the answer is simple. We just add the fourth satellite. The equation set becomes this. Now, that our position XYZ can be solved out of the equation set, and this is why at least 4 satellites are needed to complete the GPS positioning process. Besides, we can also calculate our local clock offset against the atomic clock in the GPS satellites. And this procedure is known as GPS time synchronization. Okay, let's have a quick glance at GPS satellite signal frames. Basically, GPS is BPSK signal in CA code, broadcasting at 1575.42 megahertz. The bitrate of GPS satellite is 50 bps. GPS satellites broadcast GPS signals in different frequency band and in different modulation. L1 signal is the most common signal in civil usage. The strength of signal received is very weak, at about minus 130 dBm, and most GPS receivers wouldn't work indoor. It makes GPS signal interference or spoofing quite easy, since attackers don't need to generate a signal strong enough to mask the real signal. Okay, BRDC files, which stands for Broadcast Ephemeris Data, contains the unique GPS satellite ephemeris messages for each day. Ephemeris data provides the exact location data, which is x, t, y, t, z, t, and orbit parameters of each satellite, so that receivers can get priori information in order to calculate position of the satellites. You can download BRDC archives in form of RENIX format from FTP server of NASA. RENIX stands for Receiver Independent Exchange Format. It's a data interchange format for raw satellite navigation system data. The archives are named in the folding scheme by rows in this table. Yeah, 4 digit year, 2 digit year, 3 digit day of the year compressed unit file is .z. Okay, for example, BRDC 354.0.14n means December 20th, 2014. Yeah, since December 20th is the 354th day of the year 2014. Okay, for a long time, there is only concept of this kind of GPS spoofing, and there is no available running code. But now there is one. But first, let me show the hardware platform we needed for this experiment. To transmit the signals into real air, we need software-defined radio platforms such as HackRF, BladeRF, or USRP. HackRF is an open-source SDR platform using USB 2.0 interface, operates on frequency band from 10 MHz to 6 GHz, supporting a maximum sample rate of 20 samples per second, but only half duplex. Every design detail is publicly available, from host driver to ARM firmware and even hardware scheme, and PCB layout and boom. They are all open source. BladeRF has a USB 3.0 interface, operates on frequency band from 300 MHz to 3.8 GHz, supporting independent RxTX and 12-bit quantization, and 40 mega SPS quadrature sampling and full duplex, which means it can transmit and receive signal at the same time. BladeRF seems to have a better radio frequency performance than HackRF, since it uses only one radio chip to support all the working radio frequency range. But HackRF uses some radio frequency switches and converters on PCB board to expand a narrow working frequency to a larger one, which brings quite a lot of radio power loss. But according to our experiment, both GPS signal transmitted by HackRF and BladeRF can be decoded by regular GPS receivers. We use a GPS SDR SIM project, which is an open source GPS baseband signal generator released under MIT license. The principal author of this project is a Japanese man, Takuji Ibinuma. But we have contributed codes of a static location feature, which is -L switch. And we also contributed BladeRF script support to this project. It takes a Linux, remember Linux, formatted GPS ephemeris archive and the location as input, and generates GPS baseband signal for SDR platform to playback. First, we check out the code from GitHub repo, and then compile and install this project. Then generate baseband samples according to your position using -L location switch. Finally, you can transmit through SDR devices. That's all. It's pretty simple. We also have contributed a capital R switch for HackRF project. You can use HackRF transfer program to send to TX the samples. It's very handy because GPS SDR SIM project only generates a sample of 3 minutes maximum, while GPS receivers probably don't have enough time to complete the first GPS capture process in just 3 minutes. Okay, let us see some experiment results. On the left side, it's a common serial port GPS receiver with a Linux project called GPSD. On the right side, yeah, this is right, yeah. It's an app called GPS Test on Android smartphone. As we can see, both receivers can decode the generated fake GPS signals correctly. Okay, for iPhone, when a GPS spoof starts, the positioning data of iPhone can be cheated also, even with Wi-Fi and cellular services switched on. So Apple devices seem to trust GPS data at quite a high level. In my experiment, when GPS spoofing is stopped, but without receiving a real GPS signal, date and time won't be fixed immediately according to NTP service from Wi-Fi or cellular network, which is quite uneasy to understand. When we get to the open air to get a strong and stable real GPS signal, the affection won't be fixed for at least 10 minutes, which is pretty annoying. Even we try to switch the automated timing to off and set the right time back. But when automated timing is switched to on, it would go back to the fixed time again. And this is, I think it's because GPS time cache has a long life in iPhone. Okay, then we tested the Apple Watch. The photo on the left, we can see that the date and the time of Apple Watch was cheated by GPS signal too. In this case, it's changed to December 20th, 2014, while the real local time is June 20th, 2015. And since Apple Watch is fully synchronized with iPhone, this is pretty straightforward, I think. The picture on the right shows the photos or screenshots taken with iPhone. At this time, will be inserted into a fake timestamp into the photo stream. For example, in my experiment where I take a screenshot, it just can't find it at the bottom of my photo stream. This confused me for a while. Okay, nowadays more and more mobile apps use positioning data to bring more suitable service to users. But it seems that those apps trust position data totally. For example, taxi calling apps like Uber and Didi Taxi. Didi Taxi is a popular alternative app in China. Yeah, it can be easily cheated using this GPS spoofing method. Again, this is Japan, France, and this is Didi Taxi. The left picture shows that location-based apps like WeChat, which is a popular message app in China also, will get a cheated location label when posting with geographic labels. And apps like Nike Plus Running can be also cheated too. Okay, that was GPS spoofing. Then I will introduce a cheaper method to do position spoofing with, which only needs a laptop. It's a Wi-Fi assisted location spoofing. Since GPS positioning won't work indoors, positioning service providers such as Apple Maps, Google Maps often use Wi-Fi signal to help users to get a better positioning performance. The principle is simple. The wireless chipset of cell phones collect information of all surrounding Wi-Fi hotspots. The key information to help positioning is SSID and BSSID. SSID means service set identification. It's a display name of Wi-Fi hotspot. BSSID, which stands for Basic Service Set Identification, is a MAC address of the wireless access point (AP). A positioning service provider collects SSID and BSSID against GPS data into their positioning assist database. Sometimes the information collected process is completed in user's cell phone. For example, I got a clip from Apple's website, which I quote, "These calculations are performed live on the iPhone using a crowdsourced database of Wi-Fi hotspot and cell tower data that is generated by tens of millions of iPhones sending the geotagged location of nearby Wi-Fi hotspots and cell towers in an anonymous and encrypted form to Apple." So what about we generate some fake SSIDs and BSSIDs in order to see whether those positioning service can be cheated or not? The most straightforward idea is to collect those data manually and then buy a lot of wireless routers setting the BSSIDs and the SSIDs of each router according to our needs. It will be quite a hard job to complete. So we need to come up with a more effective approach. First, we need to collect SSID and BSSID around. For Linux, we have IWUtil, which can easily collect those IDs. In order to speed up, we wrote a awk script called wifimdk3.awk to process IW output for later use. We will see the output later. If you are a user of Mac OS X, you can use airport util shipped within your system. We also have a simple but effective bash script to help you collect those data more effectively. In my case, I took a taxi to collect about 20 positions in my city. All I need to do is pressing up and enter in taxi. Okay, to complete this attack, we only need a Linux laptop with a wireless card. First, we need to install MTK3, which aims to exploit common IEEE 802.11 protocol weaknesses. Then change the following line in Makefile in order to make MTK3 compile successfully in recent operating system. And then in order to generate fake SSID beacons, we need to set up the wireless card to monitor mode. There are two ways to do this. One is using aircrackng package, and another is just using iwconfig. Okay, then the show is up. We can start the beacon flood attack using B and -V switch. Then let's see some results. We get to the position shown in the top left pin of the map to collect data. Then we get to the bottom right pin map to reply the SSIDs. Okay, this picture shows the faked position. We capture the SSIDs here. And this girl, I think, is my girlfriend. Yeah. Okay, the list is BSSID and SSID data we collected. So take a picture, please, and type them with your keyboard afterwards. I'm kidding. They will publish the material at night. You can try to do this experiment later by yourself, I think. Soon after we start the flood, a lot of faked SSIDs can be scanned using our cell phone. But those SSIDs, as we can see, cannot be attached successfully, which is as we expected. Then we opened Baidu Map. It's a popular map in China back, since we can't use Google, you know. After a while, the position is affected successfully. I do this experiment in Alibaba Group site, which is a right bottom point. Okay, that's all for Wi-Fi assisted positioning spoofing. There are also other possibilities when time is affected, such as SSL certificate. For example, we know that the expiry date of SSL certificate is very important. Attackers can use this to attempt man-in-the-middle attack. Base station frequency offset. We also found out that this GPS spoofing method can also interfere the sync signal of cellular network base stations. Most base stations in cellular networks rely on PPS, which means pulse per second signal, which derived from GPS signal to calibrate frequency offset. We transmitted fake GPS signal, which contains a high error PPS signal. Then the LTE base station automatically sync with this PPS signal, and the whole LTE network's frequency error increased for about 5 Hz to 11,000 Hz, which can cause the base station failing to work. And NTP services provide time synchronization services through internet connection. Most of NTP services use GPS time as their upstream source. If NTP service is affected by effectors, I think the impact would be enormous. So we will give some suggestions on positioning security for developers. One, you can add a position and daytime check based on continuous principle. Position and time hooping should be verified or warned to users in mobile devices. Two, add a separate clocking hardware module, for example, in Apple Watch. 3, decrease the cache time from GPS positioning signal. According to our observation, the cache time of GPS position data should be decreased, since it's not appropriate for a faked GPS position to be cached for a long period. And 4, add a manually refresh GPS cache function. I think it is necessary to provide a forced refresh function for positioning data when user find out that position data is suspicious. And 5, add a high priority time sync device based on NTP over SSL, for example. And since internet connection is more reliable for mobile devices, an authoritative NTP over SSL time source should be lifted to a higher priority in mobile system. And 6, GPS signal strength detect. Fake GPS signals are often much stronger and much more uniform than real signal, as is shown in this picture. Abnormal signal strength could be used as a detect identification, I think. The last one, Wi-Fi positioning data provider should do cross verification for their database in order to exclude fake samples. You know, you should never trust users' input. Okay, in conclude, we have introduced 2 methods of position spoofing. It's important for developers and vendors to examine position time data more closely and more frequently and more effectively. As a basic security principle, any user input shouldn't be trusted completely. Besides, we have also submitted the relevant technical details to Apple product security team. We would also like to thank Dr. Yang Bo of CITR China Academy of Telecommunication Research for his work on frequency offset interference of base station. We'd also like to thank Tuna Association of Tsinghua University for the help on some experiments. Okay, that's all. Any questions? Okay.
Out of the 3 cards that you have, which ones work the best for your effort?
Switch card.
Yeah, the SDR. So
Okay. Maybe this one. I think Blade RF works better. I think because the RF performance is better than Hack RF, but Hack RF has a lower price and open source blood, I think. And the USRP of this the type is B210. I think it's very expensive than other two. Okay. You please. I think you.
What is a radius this kind of cards can spoof?
It's what range?
Yeah. The area you can spoof is
area. I think the whole.
1 kilometer, 10 kilometers.
No, not that fast because we haven't tried in a high antenna. I think if you use a high antenna and strong strings, I think that is enough to cover a like 10 or kilometers, I think. Because GPS signal is pretty low at about minus 130 dBm. It is below the noise level, I think. So it is very easy to be interferenced. Okay. Hi. Okay. I think later you can, after you get this material, you can do the Wi-Fi positioning spoof experiment just in your Linux laptop. It's very simple, and you can try to collect these points. I think in Netherlands, when you get back to the US or to other country, you can just fake the position. Okay. GLONASS. Actually, the BRDC data supports GLONASS because this one, N stands for GPS, and another character stands for GLONASS satellite. I think it's very simple to do this. Okay, there's another 2 minutes. Maybe any other questions?
No, quick live demo.
Quick live demo? No, today. But I think it's very simple. You can do it by yourself, I think. This I think is very easy to do. Oh, hi.
So what would be the approximate cost of setting this up?
Cost, you say?
Yeah.
For Wi-Fi, it costs nothing. It's $0. No. Wi-Fi spoofing doesn't need SDR devices. SDR for HackRF, I think it's about $300. You can buy it from Great Scott Gadget. And Blade RF, I think it's about $400 maybe. And for Blade RF, for USRP, it's great. It's more than that. I can't remember actually. 15 gigahertz.
Yeah, the GPS signal is 15 gigahertz.
No. GPS signal is 1050 and 75 point another megahertz. It's 1.5 gigahertz, not 15 gigahertz. Okay. Actually, the frequency transformation is a traditional communication method. About 15 gigahertz or 50 gigahertz, it can be handled using a transformation, such as some radio components. It's very simple. So the gigahertz number, you can just see it's a very large number. Okay. Okay, I think time is up. Oh, one last question maybe.
Maybe I missed that in the beginning, so I'm sorry. But did you also, in your research, take a look at the military-grade GPS and how hard that would be?
Actually, GPS documentation is very in detail, I think.
Yes. For the US military GPS signal?
No. That is PY code, I think you said. It's PY code. Yeah?
Now, I was just wondering, while listening to your talk, that how hard it would be for somebody to attack this if it's still secure enough.
Actually, someone has already done this, I think. Everyone is doing this, I think. It's not that, but they use some method to change the cipher frequently, I think.
So the technique will still work, but you need to know, because if the original GPS signal was the highest precision, but they actually introduced the error, so the civilian wants not to be precise. So if you know the codes to get back to the original one, then the technique still holds.
Okay. So to jam that, or not to jam, but to store it, you need the
examples you use for the.
Okay. Linux example, okay. Yeah, this one. Okay, thanks.